So, hello everyone. Welcome to this week's SMaRT seminar series. It is my pleasure to welcome Dr. Kshitiz Upadhyay, who is an assistant professor in the Department of Aerospace Engineering and Mechanics at the University of Minnesota Twin Cities. He directs the Soft Materials Mechanics Laboratory over there. His research focuses on mechanics of soft materials with emphasis on constitutive modeling, data-driven methods, experimental solid mechanics, and injury biomechanics. Dr. Upadhyay's work has been supported by NSF, the Office of Naval Research, and the National Aeronautics and Space Administration. His research has been recognized through multiple honors, including the Early Career Research Award from the World Council of Biomechanics and the Best Dissertation Award from the Department of Mechanical and Aerospace Engineering at the University of Florida in 2020, and the Gator Engineering Attribute Award for Professional Excellence in 2020 also. Before joining the University of Minnesota Twin Cities, he served as an assistant professor in Louisiana State University and as a postdoctoral fellow at the Hopkins Extreme Materials Institute at Johns Hopkins University from 2020 to 2022. And with that brief introduction, please join me in welcoming him for this presentation today. Thank you for joining us, Dr. Upadhyay, and the floor is all yours.
Thank you, Dr. Goswami, for the introduction. Let me share my screen. All right, can you guys see my screen?
Yes.
All right, awesome. Well, thank you for inviting me to give this seminar at the joint webinar organized by Johns Hopkins and IIT Delhi. Let me briefly mention my connection with Johns Hopkins, which Somdatta also touched upon. I did my postdoc at Johns Hopkins from 2020 to 2022 with Professor K.T. Ramesh at the Hopkins Extreme Materials Institute. So I have a close connection with Johns Hopkins, and a large part of the work that I will present in this seminar was at least started or completed at Johns Hopkins during my time as the postdoc there. So, as mentioned, I'm an assistant professor in the Department of Aerospace Engineering and Mechanics at the University of Minnesota, where I direct the laboratory for soft materials mechanics. As the name suggests, we study the mechanics of soft materials like foams, elastomers, and tissues that show large complex deformations. In this particular presentation, I'll touch upon the topic of data-driven mechanics. So I'll discuss how machine learning is allowing us as opening up new ways to understand soft materials and how it's transforming solid mechanics as a field in general. I'll do this by going through two specific examples from my research. And in the last part, I'll do a look ahead into the future emerging opportunities in this space. All right, so before I dig deep into my research, let me start by explaining what soft materials are. So soft materials represent an emerging class of materials which have a variety of applications across areas such as aerospace, as lightweight space structures, in defense, as foams and lattice structures for impact attenuation applications. In the field of robotics, these soft materials are being investigated for their potential use as lightweight compliant robots. And from a mechanics perspective, even human tissues and organs are considered modeled as soft materials. So with all these applications in mind, the understanding of the mechanical behavior of soft materials is important, not just for the evaluation, design, and analysis of these structures of soft materials, but also for the discovery of new soft materials with tunable material properties, for example, and optimized mechanical behaviors. From a biomedical perspective, understanding the mechanics of soft materials is important in the injury biomechanics community because the mechanics governs the injury of many organs. For example, traumatic brain injury of the brain happens when the brain is deformed beyond certain limits. Now, with all these critical applications, the mechanics of soft materials is very complex. soft materials inherently show large deformations, nonlinear stress strain responses, viscoelasticity, which means time-dependent mechanical behavior, as well as temperature-dependent mechanical behavior. And especially tissues and organs, which are living materials, show features such as growth, repair, and remodeling, which are together makes it a very complex mechanical problem. So with these applications and opportunities in mind, my laboratory at the University of Minnesota focuses on developing new methods to understand the mechanics of soft materials under a variety of loading and temperature conditions. We work on all the four pillars of mechanics, but focus on the interface between analytical and data-driven mechanics. On the experimental side, which is our minor component of our research, we develop new tests to investigate the high strain rate behavior of soft materials. For example, this video shows a Kolsky bar experiment where the top plate is moving at a high speed, 15 meters per second, and shearing the soft materials. And we are using DIC to investigate the strain response of the material. On the theory side, we develop constitutive models, which are equations that govern the stress-strain responses of soft materials. And on the computational side, we then use this theory to develop models that can then simulate the responses of these structures under complex loading conditions or more real-life loading conditions once we have the theories ready. Machine learning permeates every part of my research and allow us to accelerate our experiments, to make our constitutive models more flexible, and to make our computational models more efficient. Of course, none of this would be possible without my graduate students and the funding, for which I'm very grateful. So in this talk, I have three parts for you. In the first part of this talk, I'll discuss one example from my research at the interface of theory and machine learning. Okay, so theory and machine learning would be the topic of the first part. And the second part, I will discuss my research at the interface of computations and machine learning, specifically the development of surrogate models and understanding of uncertainty in computational models. All right, so let's start with the first part, which is on the interface between theory and machine learning, specifically on data-driven constitutive modeling. All right, before I talk about the data-driven aspect of it, let me start by refreshing our memories of what a constitutive model is. So in general, the mechanics of any material is defined or governed by several field equations. Any thermomechanical system is governed by these five field equations, which come from the conservation of mass, the balance of linear momentum, and the conservation of energy. Now, against these five equations, there are 16 unknowns. So the evolving density, the stresses in the body, the specific internal energy, temperature, position, heat flux, and the specific entropy. All of these are unknowns that we don't know. Without them, we can't simulate the mechanics of a system. And so you can see that this system is inherently underdetermined, and we need some extra equations to balance this system. Those missing 11 equations that are required to describe the response of a material is called constitutive model. Okay, so in general, or in total, there are 11 such constitutive models, 6 equations for stresses, which are called the stress-strain relationships. For example, the stress can depend on other factors as well, such as temperature and strain rates. There are 3 equations for heat flux, 1 for temperature, and 1 for the specific internal energy. In this presentation, I'll focus on the development of constitutive models of stresses. So how stress relates to the loading conditions. All right, so now that we have seen what are constitutive models, let's see how people propose one. So the field of constitutive modeling has a long history, at least spanning 350 years. And the earliest phase of constitutive model I call the classical constitutive modeling phase, where the general method of proposing a constitutive model was to observe material response and then propose a simple equation. Hooke's law is a classical example, which was proposed by Robert Hooke by running experiments on metallic springs, which he wrote down in his diary as a Latin anagram, and later decoded it 2 years later when he first published the Hooke's law, and that said, ut tensio si quis, which means as the extension, so the force. Okay, so these types of simple constitutive models based on observation of material response worked well for us for several centuries, but they got a facelift in the 1950s when researchers of the likes of Clifford Truesdell, Walter Knoll, Bernard Coleman, over a series of publications, developed what's called the theory of constitutive modeling. Now, their method of developing constitutive models was different than the old way. They started, they say, they told us to start not from the material response, but from a generalized functional constitutive equation, which is generally derived from the second law of thermodynamics in what's called the Coleman-Knoll procedure. Once you have the generalized functional constitutive equation, the next step would be to impose certain constraints on the generalized form to ensure physical behavior. So you start from a generalized model that can govern the response of thousands of materials, and then you narrow down the possible constitutive models. And only in the end, you apply some simplified assumptions based on the observation of material response, and that leads to a specific constitutive model. An example can be thought of from the world of hyperelasticity, where this is the generalized functional form, where stress is related to the strain energy density and the right Cauchy-Green deformation, which can be thought of as a strain tensor. Now, this is a generalized functional form. The specific model would have some equation for the strain energy density function. It's not that. And so the second step would be to impose certain constraints on the constitutive equation. For example, if we expect the material to be isotropic, then we can replace the right Cauchy deformation tensor with certain invariants, such as certain scalar invariants, which narrows down the set of possible constitutive models. Only in the end, we would observe the material response and propose a constraint equation, such as this neo-Hookean model, where it was assumed by Taylor that the strain energy density is just a function of the first invariant. Now, this theory of constitutive modeling has worked well for us for over 75 years now and still works. But with the growing popularity of machine learning methods, a new wave of constitutive models appeared in the early 2000s, which were mostly data-driven in nature. So some of the researchers went back to the old way of observing material response, and this time letting machine learning regression methods propose an equation rather than humans proposing an equation. And so we see these types of models, which are simple mappings between strain and stresses, black box mapping without any understanding of physics. Now, the good thing about machine learning regression methods is that they are very good at fitting the response. But the bad thing is that outside the training regime, they can predict some bonkers response, right? So there is no physical meaning. The machine learning models by themselves don't understand physics. And so the latest paradigm in constitutive modeling has been that of scientific ML, or physics-informed machine learning, where researchers are exploring different ways in which they can impose physics or physical knowledge into the constitutive equations to make them more generalizable and more interpretable. Now, there are several ways to do this, and several different strategies has been applied. But one strategy that we use in our lab is to go back to the Coleman-Knoll procedure, starting with the general functional equation, imposing physical constraint like the Coleman-Knoll procedure, and only in the end using physics-informed machine learning to propose a constraint equation. So this is the framework that I'll discuss in this talk. The specific problem that I'll look at would be that of viscohyperelasticity. Okay, I hope. Okay, so of short-time viscohyperelasticity, which is basically the mechanical responses of soft materials when they undergo large deformations and very rapid loading. These type of phenomena are very important in the case of injury biomechanics to understand what happens to the organs and tissues with traumatic injuries, and also in the area of energy absorbing materials that are used to make protective equipment. All right, so let's start with the phase one of the constitutive modeling, which was to start with a generalized functional form. So this is the generalized functional form of short-time viscohyperelasticity, where stress is an additively decomposed function of volumetric stress, hyperelastic stress, and the viscous overstress. The volumetric stress depends on a volumetric energy density function. The hyperelastic stress depends on a strain energy density function, and the viscous overstress depends on a viscous dissipation potential. The first two components capture the quasi-static response of the material, and the last component captures the dynamic high strain rate behavior of the material. Now, as I said earlier, this is a generalized form, and it has its roots in thermodynamics. In fact, the quasi-static portion comes directly from the Coleman-Knoll procedure, and the dynamic portion comes from a statistical thermodynamics argument. It was first proposed by Morris Byatt in the 1950s. So this is a generalized form. It's not a specific form. That means we are not yet proposing any specific equations for these energy density functions and potentials. Examples of available potentials in the literature are here. These are some of the available potentials available in the literature, and these are analytical models. Now, in the spirit of data-driven modeling, we will stay away from these fixed functional form. Rather, we will learn constitutive models using machine learning methods directly from the data. All right, so these available potentials, like this generalized framework, has been used in the literature to describe the mechanics of a wide range of materials, both biological and synthetic materials. Now, now that we have understood the generalized functional form, let's move on to the second stage of constitutive modeling, which is the imposition of physics-based constraints. Now, because we started from the theory of constitutive modeling, a number of constraints are actually built in to this form. For example, objectivity is built in because both the tensors S, which is the second Euler-Kirchhoff stress, and C, which is the right Cauchy-Green deformation tensor, are objective tensors, and they are invariant to the changes in reference frames. Also, balance of angular momentum is satisfied a priori because the second Euler-Kirchhoff stress tensor is necessarily symmetric. Isotropy is not there by default, but we can, if we assume isotropy, we can replace the strain and strain rate tensors with certain invariants of these tensors. We have these invariants J, which is volumetric strain, I1, I2, which are strain invariants, and these J series of invariants, J1, J2, which are all joint strain and strain rate invariants. Of course, this framework is not tied to isotropy, but for the purposes of this presentation, I'll assume isotropic response. Right, now these constraints are already built in, but some other constraints are not built in. We have to add them, such as normalization condition, which makes sure that the stress at zero strain is zero. And finally, the second law of thermodynamics. Now, that is built into the quasi-static component, but in the viscous overstress component, we have to make sure that the dissipation or the internal entropy generation is non-negative. Okay, so these constraints are not there, and we will try to add them using the chosen machine learning framework. All right, so before we move on to the third stage, which is to actually use machine learning, let me do one more mathematical operation, which is basically solving these partial derivatives using the chain rule. So when we solve these derivatives with the chain rule, we get an alternative generalized functional form of this that looks like this. Here, each of the stress components is an additive decomposition of the product of certain response functions and certain integrity bases. Okay, so this is obtained by when you open up these derivatives using chain rule. Here, response functions are functions of invariance. Okay, they can be some functions of deformation, and this is what defines a constitutive model. See these deviatoric components, these are just these integrity bases, they are just dependent on kinematics. Okay, so this is kinematics dependent, and it is the response function that makes a constitutive model a constitutive model. And so we see in all the available constitutive models, hyperelastic, viscohyperelastic in the literature, these response functions have some fixed equation. Take Mooney-Rivlin model, for example. In Mooney-Rivlin model, gamma 1 is given by this equation. It is a function of certain model constants and invariants. But what's noticing here is that this is a fixed equation. Okay, it's not flexible. It's a fixed equation. So at this point, I will invoke machine learning methods to learn this gamma 1, gamma 2, zeta 1, all these response functions directly from experimental data without assuming any mathematical form a priori. Okay, so this point I'll call machine learning. After we have done all the heavy lifting using continuum thermomechanics. All right, so to summarize, we have these three stress components all given by certain response functions, and there are these constraints that we want to impose. As a machine learning framework to learn these response functions, we use Gaussian process regression. Uh, Basically, we have three Gaussian process regression models, two unconstrained, one constrained. The first two Gaussian process regression models capture the volumetric stress and the hyperelastic stress. So the first model is a mapping between volumetric strain and the response function. Second GPR model is the mapping between the strain invariants and the corresponding response function. And the third GPR model relates to the volumetric stress and its corresponding response functions. Now, the reason we choose Gaussian process regression is because it is an exact inference method. Okay, what it means is that we can make sure that GPR always exactly predicts the value of the training data points. And using that property, we can impose the normalization condition just by including zero stress, zero strain condition in my training data. So if I have zero stress, zero strain in my training data, this normalization condition holds true. The inequality constraint is not there built in standard Gaussian process. And for that, we use a constraint Gaussian process regression model, which imposes this constraint of non-negative viscous dissipation. All right, before we look at the results, let me quickly go through what GPR is, because it's a scientific machine learning conference. I thought I should talk a little bit on machine learning methods. So standard GPR, it's basically a non-parametric regression method that uses Gaussian processes to fit a data. Gaussian processes, you can think of them as a distribution over function. It's a infinite dimensional generalization of a multivariate Gaussian process or Gaussian distribution. GPs are fully defined by two numbers, one mean function and one the covariance kernel. Usually we assume the mean to be zero. In this research, we assumed the covariance kernel to be a Mattern kernel, which is governed by two hyperparameters, sigma and L. These hyperparameters make GP a GP. Okay, so when I say I fit a GPR to my data, all I mean is that I'm maximizing this log marginal likelihood to find the optimal hyperparameters that describe my data. All right, so this is standard GPR. Now, constraint GPR can add some constraint to the predictions of the GPR model by adding the constraint evaluated at several points along the space, the input space, as soft constraints. So for example, here, this constraint G of f of x has to be greater than or equal to 0 was added directly in the optimization. So it becomes a constraint optimization problem. And this constraint was evaluated at several points called constraint points. So you can see that it's a soft constraint. It's not a hard constraint that is built into the mathematics of the GPR model. All right, so now that we have seen how we train standard GPR model, constraint GPR model, let's look at some results. So the first results I'll show you is from the first GPR model. Because the three GPR models are independent, we can evaluate them separately. In practice, they would have to be combined together to make a holistic viscohyperelastic model for soft materials. So this first GPR model is a mapping between J and the corresponding response function. Of course, once you get the response function, you can recreate the volumetric stress. So to train the model, I used this confined compression deformation data, which is synthetically generated using a known constitutive model. Here, this is the x-axis is the volumetric strain J, and the y-axis is the axial stress. So as you compress the material, the volume reduces and the material develops its axial stress. Okay, so I fit my model with this data, and the model works really well, right? But that is expected from machine learning model. They do very well in the training regime. Now, what's the actual test of this model is whether it performs well outside the training regime. So for that, I evaluated the predictions of this data-driven constitutive model up in confined tension. Okay, so confined tension wasn't used in training. So here, this blue line is the ground truth. So this is the ground truth. This is the ground model, what we know about the material. And this red is the prediction by the data-driven model. So really good. We also compared the predictions with an analytical model, a traditional constitutive model. So for that, we use Neo-Hookean model calibrated it with using the confined compression data, and then predicted the stress response under tension. And as expected, the Neo-Hookean model makes a reasonable prediction. What I'm more focused here is not on the accuracy of the prediction, but rather whether the responses are physically meaningful or not. Finally, we compared this prediction with a black box machine learning mapping, which is from the third stage of constitutive modeling evolution I talked about today, simple mapping between strain and stresses, which was also trained using the confined compression deformation mode. Now, clearly we can see that it doesn't predict a correct response of the material under tension, and that's because tension wasn't used in the training regime, and this model doesn't understand physics, so it is predicting some damaging response in tension, which is not physically reasonable. Okay, so what this tells us is that our proposed data-driven surrogate model makes physically meaningful out of sample prediction, just like an analytical model. So it is behaving like a theoretical model, like Neo-Hookean and Mooney-Ribble, like those models, right? So it has all these advantages of traditional models, but at the same time, it has the benefits of machine learning in that the model can be learned directly from the data, and there is no expert intervention needed. Now, this is a big plus because traditionally, whenever we do experiments on soft material, there has to be an expert judgment into what is the proper constitutive model to be used, whether we should use Neo-Hookean model or Mooney-Rivlin model, Yo model, Gent model. There are just many models that are available, but not with data-driven approaches. Here, you can learn the model directly from the data, and there is no expert intervention needed. Also, because of the flexibility of machine learning regression methods, this model fits to any type of nonlinearity. So it's a one-size-fits-all type of approach. And finally, I just trained this model with 26 data points. So it is pretty much compatible with small data. So this shows that there is this possibility of combining the benefits of theoretical modeling and machine learning, and this is what this proposed model shows. All right, so now that we have seen the performance of this volumetric part, let's quickly see the performance of the hyperelastic part of the model, which I trained using data from uniaxial tension deformation mode, again synthetically generated, and I then predicted the response under compression deformation. Again, blue is the ground truth, red is the prediction by the data-driven surrogate model, and we see that the model prediction is reasonable. Now, again, I would re-emphasize that I'm not looking at the accuracy. The compression response wasn't used in training, so there is no reason to expect that it would be spot on in compression. What we are more concerned or more interested in is whether the mechanical response is physically meaningful, because that's what we want for a constitutive model. We not break any physical expectations outside the training regime. And that's what we see by the surrogate model. It is predicting a reasonable response. It is showing compression tension asymmetry, which is very commonly seen in soft materials, in that the compression response is much more stiffer than the tensile response. When we compare this result with an analytical model, we used Yo model, for example, it also predicts a reasonable response, and which is expected from an analytical model, right? But the interesting thing here is that the data-driven model also behaves like an analytical model. At the same time, it brings all the benefits of machine learning methods in that it is automated and fully data-driven. All right, finally, we compared the results with this black box mapping, and you can see that it makes an unreasonable prediction, right? It makes a convex down response where this is how it should be. So it's not a good prediction by the black box mapping. We also tried to evaluate the predictions of our model in shear. So shear is a completely different deformation mode now. So it is not even uniaxial. And so in shear, we see this is the predicted responses by the surrogate model and the Yo model are very close to the ground truth. So they are both doing very well. So the surrogate model is working like an analytical model with all the benefits of machine learning. But the black box mapping here, you can't even see it because it predicts zero stress always. So black box mapping predicts zero stress because shear stress wasn't included in the training data. But the data-driven model is very data efficient. It doesn't need shear data. And just with uniaxial data, it can be generalizable. All right, finally, let's look at the viscous overstress part of the model. Here, I trained the model using uniaxial tension data across multiple strain rates in tension, and then applied it to predict mechanical response under compression. And as expected, both the surrogate model and an analytical model, this time we use a standard model called the Pioletti model, they both predict reasonable responses under compression. Now, this time you don't even see the black box mapping model here because it was predicting a tensile stress under compression, which is totally unreasonable and impossible. So on closer investigation, we found out that that was because of this negative dissipation that was predicted by the black box mapping, which is not possible. Now, because our model understands physics, it understands that the dissipation has to be positive. It doesn't make such mistakes, and it makes reasonable predictions far outside the training regime. And we also tried to observe the mechanics, the predictions for noisy data to mimic more similar to what a real experimental data would look like. And as expected, the GPR models do exceptionally well with noisy data. All right, so far we have seen how the integration of machine learning and classical mechanics can open up new ways to develop constitutive models for materials which are not only flexible and generalizable, but they are fully automated and data-driven. And this is opening doors for automated model discovery. So the next application that I will talk about in this talk is on computational modeling, which is the next step of constitutive models. Once you have the equations ready, then you feed in those equations into computational models, and you can then predict the response of a structure under any loading condition you want. Here I will talk specifically about this issue of uncertainty. So how to compute uncertainty in high fidelity computational models. And this work was done in collaboration with Mike Shields' lab at Johns Hopkins, also with Dimitris Giovannis. All right, so the specific problem I will touch upon here is that of computational modeling of traumatic brain injury. So traumatic brain injury is a debilitating condition that happens when brain or your head is either rapidly impacted, undergoes rapid motions, or even if it incurs a blast loading. So all these conditions lead to neuropathological symptoms that are collectively called traumatic brain injury. In the US alone, traumatic brain injury leads to almost or more than 200,000 deaths, 200,000 hospitalizations and 77,000 deaths in the US. So it's a pretty big problem in the US, but also across the world. And computational models are very useful in TBI research because they give us a window into seeing how the brain, which sits inside the skull, deforms to all these loadings. And once we know that the deformation, we can have a sense of the injury susceptibility because the actual deformation, the stretching, shearing of the brain tissue has been correlated to injury and the neuropathological outcomes. So that's why these computational models are really useful for traumatic brain injury research. So during my postdoc at Johns Hopkins, I developed these head injury models using personalized data from human subjects. So we did this for several human subjects. So a human subject would be taken to a magnetic resonance imaging scanner, the MRI scanner, to get the computational head geometry of the head. We would also do MRE, or magnetic resonance elastography scans. So MRE gives the brain tissue properties across the full brain, so it gives full field mechanical properties of the brain tissue. Now, using the raw MRE data, you can calibrate viscohyperelastic model parameters. Now, these can be the traditional analytical model parameters, or these can be the new JPR hyperparameter that I showed in the first part of my talk. In this particular research, we used analytical model. Once we have the properties and the geometry, we have our full computational model, then that we can use to predict the strain fields in the brain to any loading condition. So this video shows the axonal strain fields, which is the strain in the direction of axons in the brain under a rapid head motion, like saying no. Okay, so it's a neck rotation about the inferior superior axis. So a motion like saying no. Okay, so this is what our model predicts under a certain loading condition. Now, how do we validate this model, right? How do we know whether this model is predicting right or not? So for that, we took the same human subjects to a neck rotation device. On this neck rotation experiment, their head would rotate with the same loading condition as our computational simulations, and using a method called tagged MRI, in collaboration with Professor Jerry Prince's lab at Johns Hopkins, we measured the strain fields in the brain under the same loading condition. By comparing the strain fields in the brain from tagged MRI, which is experimental, and the predicted strain field, we validated our models, and the results were pretty promising. So for all the human subjects, we could relatively accurately predict the strain fields in the brain to this kind of loading conditions, also a different loading conditions we evaluated. So we want our models to be accurate, right? But what we also want our computational models is to be reliable. And uncertainty quantification is a big part of that, especially because all the major inputs of a computational head model or any computational high fidelity model are have a lot of uncertainties, can have a lot of variabilities in the input, which trickles down as output uncertainty in the output of the computation model. Uh, so So during my postdoc, I developed a method, a data-driven method for uncertainty quantification of head models, where we can, by studying the variability in the inputs, we can find out how much the uncertainty would be on the strain fields and the injury metrics that can be computed from the strain fields. Okay. Now, this method is general, but again, for this presentation, I'll show a specific case of this method where I'll assume a 2D subject-specific constitutive head model. Sorry, so 2D head model. This is a 2D slice of the 3D model that I showed you in the last slide. And the specific strain field that we will be looking at is called MAS, which is the maximum axonal strain. So at each data point, that is the maximum axonal strain across the entire loading condition or the loading duration. For the purposes of this presentation, I will assume that the geometry and loading conditions are deterministic, and the only parameter that is variable is the material parameters. Now, as I said, this is a 2D subject-specific head model. There are 4 parenchymal brain tissue regions in this model: corona radiata, deep gray matter, cortical gray matter, and the corpus callosum. And the material properties of these 4 regions was obtained using in vivo MRE. Now, we used an analytical constitutive model which has 4 parameters. For this presentation, there is no need to go into the constitutive modeling aspect, but you can just think of these 4 parameters are the material parameters for each of the tissues. So there are 4 model parameters and there are 4 regions. So in total, there are these 16 input variables that can cause uncertainty in the output. All right, so this is what the system looks like. Now let's look at what are the challenges in uncertainty quantification. So the reason I had to develop a data-driven uncertainty quantification framework is because traditional Monte Carlo type uncertainty quantification was inadequate for this problem. So let's look at what the traditional UQ is actually. So in a traditional UQ framework, there are 3 steps. The first step is modeling the system. I already showed you before, we have a 16-dimensional input, 16 sets of material parameters, and we have an output of 2,700 dimensions. So these are 2,700 data points. Each point can have a different strain value. Now, once we have the system, the second step in UQ is to create system realizations. Now, realizations just means copies of the computational model. So we have to create somehow copies of the head models with different sets of input parameters that are usually sampled from a probability distribution. Once we have these different realizations of the computational model, the last step is to propagate uncertainty by running simulations in a Monte Carlo fashion. So running many simulations, and eventually, when the simulations converge, calculating the uncertainty parameters such as standard deviation or coefficient of variation. Now, why this method cannot work for head injury models or high fidelity modern computational models in general is because, first of all, the probability distribution of the input is unknown. Okay, so we don't know the input probability distribution of the input parameters, how those 16 parameters vary with respect to each other. Assuming, even if we know it somehow, Monte Carlo simulations usually take thousands or hundreds of thousands of simulations to converge. And these models are very computationally expensive. A 3D model actually used to take 9 days to run on a HPC at Hopkins. Even a 2D model used to take 7 hours on an HPC. So running hundreds of thousands of simulations is not possible. And for that, to avoid the high computation costs, people usually train surrogate models, which are low cost approximations of full computational models. But training surrogate models when the input and output dimensions are very high is very challenging for reasons collectively called the curse of dimensionality. So I developed a method which overcomes these three challenges and allows uncertainty quantification in head injury models. So the first challenge was the probability distribution of the input, right? So for that and creating the system realizations, I used this method published in 2016 on manifold learning-based data-driven sampling. It's a two-step process. The first step is probabilistic modeling using Gaussian kernel density estimation. So this cartoon shows a 1D example where a complex probability distribution was learned using many simple Gaussian distributions. So using this Gaussian kernel density estimation, we could get the probability distribution of the 16-dimensional input parameter. The second step of this manifold learning data-driven sampling is to then combine dimensionality reduction using diffusion maps, which reveals the local complex structure of the data, and sampling using Markov chain Monte Carlo based on reduced stochastic differential equations. So on the left-hand side plot, plot shows the distribution of two model parameters. So eta and k1, these are two parameters of this corona radiata region. You can see these are all the data points, 1 point for each data point on the brain tissue. And the structure is complex, right? So it's not a very straightforward structure. And this is actually a 4-dimensional plot. So I can only show you a 2-dimensional projection. So this is the data that comes directly from our experiment, from in vivo MRE. When we use this method of Susan Gainham, we got these new realizations, right? These realizations lie right on top of the in vivo MRE data. That means the approach was able to get the probabilistic modeling of the input data. So this method helped us create multiple realizations that follow the distribution of mechanical properties from in vivo MRE. Using this method, we created 300 realizations of the system. So you can think of them as 300 computational models. Each model has a different set of 16 material parameters, and those material parameters are obtained using this manifold learning-based method. Once we have those 300 sets of models, the next step was to train a surrogate model. Now, as I said, surrogate modeling is difficult here because the input and output dimensionality are very high. So for reducing the dimensionality of the output, we use this method called Grassmannian diffusion maps, which was invented by Dimitri Strivanis and Mike Shields of Johns Hopkins in 2020. This method is a two-step dimensionality reduction method. The first step, the full output, so in this case, the full strain fields are projected down to a Grassmannian manifold using thin singular value decomposition, which is a linear dimensionality reduction. And the next step, diffusion maps, is run on the reduced data, on the first step of reduced data. So this two-step dimensionality reduction method reduces the dimensionality of the strain fields down from 2700 to actually 3 to 5. So these 3 to 5 numbers would now represent the information in the full strain field, which is a huge dimensionality reduction. Once we have the reduced data, we used GPR, or Gaussian process regression, to train this model between input and the reduced output. And we also trained a geometric harmonics model to recreate the full data by training a model between the reduced output and the full field strain. Together, the GPR and the geometric harmonics model create our full surrogate model, where if you now have any set of input parameters, you can find out the full strain fields using these two surrogate models. Okay, so now that we have seen what this model looks like, let's evaluate it. Let's see whether the surrogate model is any good. So this, on the left-hand side, you see the strain fields predicted by a certain set of material parameters not used in the training data. And the right-hand side, you see the surrogate model prediction. Pretty good. when we evaluated the accuracy using leap and out cross validation, we found a 93% accuracy. Now, not only these fields are accurate, but we also found out that we get almost a million times cost reduction. The surrogate model used to give predictions in 10 milliseconds, which is a huge reduction from the hours that computational model used to take, even on an HPC. And surrogate model, I'm talking about running on my laptop. Okay, so surrogate model provides an accurate and significantly low cost approximation of the computational model. And so using this surrogate model, we propagated uncertainty and calculated a coefficient of variation as an uncertainty metric. So we can, now that we have the surrogate model, we can run it tens of thousands of times. So we did it, calculated the coefficient of variation, which is a measure of uncertainty across the strain fields of the human brain. Here, the green regions are regions of low uncertainty, the yellow regions are regions of high uncertainty. And we found out that the regions of low uncertainty also correlate with the regions of large strain in the brain. And what this told us is that when we investigated the uncertainty of different percentile strains. So for example, here, 50th percentile strain is the value of the strain that is greater than 50% of all the data points on the brain tissue. And this was important to us because 50 and 95th percentile strain is used as an injury metric in the literature. So we use this 50th percentile and 95th percentile strain values as a predictor of the susceptibility of the brain to injury. And so this research told us that among the two injury predictor variables, the 50th percentile is actually associated with a higher uncertainty. So it was a useful information. All right, so in these first two parts, I have shown you how machine learning and mechanics can be integrated to give us better constitutive models and also to make our computational models more usable. So in the last part, which I'll try to finish quickly in 5 minutes, is I'll talk about the emerging areas at the intersection of my mechanics and ML. The first area that I'll talk about is very close to what I talked in the first part of this talk about the integration of theoretical modeling with machine learning. There has been a lot of research going on into integrating theoretical knowledge into machine learning frameworks to build these data-driven models that are reliable and can open the doors for high throughput characterization and materials discovery. I feel that this type of work needs sustained effort in both the theoretical modeling and the integration of data-driven. We can't just focus on data-driven, in my view. Theoretical models give us knowledge about the physics behind the different mechanics problems and also give us the knowledge about the constraints that the mechanical models should obey. And my lab works on this philosophy. For example, on one hand, we are developing models that can capture damage in soft materials using this framework called energy limited hyperelasticity. But on the other hand, we are then using our knowledge of damage from theoretical models to then make them more flexible and learning these different components of the damage model directly from data, enhancing the flexibility and accuracy of these models. And the results have been promising. We see that the data-driven models are performing better outside the training regime than the normal analytical models. Now, this is not the only way to approach scientific ML-based constitutive modeling. And different people are trying different ways. For example, there have been research on the use of ANN for thermoelastic modeling. This is the work by Professor Lagudas from Texas A&M. We have also used LSTMs, which is a type of RNN for learning viscoelastic response, more long-time response of soft materials. And this presentation would be incomplete if I don't talk about the unsupervised model discovery methods. So some researchers are developing a class of methods where the constitutive models can be directly learned from full field data without requiring stress-strain pairs. And one method that is very popular is called Euclid. It's based on a sparse regression modeling approach. So all of these are different ways in which we are approaching this problem of scientific ML-based constitutive modeling. The second emerging area I would talk about is the integration of machine learning with computational mechanics, again, which I talked about in the second part of my talk. Modern computational models, we all know, are getting more and more expensive, more and more high fidelity, more and more complex. And it is not uncommon for us to see computational model running for days, even on a supercomputing cluster. Example is from my research where a 3D model used to run for 9 days on a supercomputing cluster. Now, this is not good for the translation of these models because we want these models to be used someday by doctors, right? But if someone comes with symptoms of concussion, the doctor won't shouldn't say, "Oh, let come after 9 days, and I'll tell you where the injury is," right? So, this high computational cost diminishes the actual translation, actual applicability of our computational models, and this is where machine learning and data science methods are helping us build more efficient surrogate models that with some loss of accuracy, some loss of fidelity, we are able to develop these models that are much faster, opening doors for real-time decision making, uncertainty quantification, and in general, getting more insight from the computational models. And this area has been investigated both in the fluids and the solid mechanics domains. In the fluids domain, for example, this method called SIND, which is sparse identification of nonlinear dynamical problems, is making waves in CFD simulations, making them very, very fast. There have been research on the integration of dimensionality reduction and regression methods also for fluid mechanics simulations. In the area of solid mechanics, PIN or physics-informed neural networks have been used not only to discover PDEs, but also to solve PDEs and run these complex simulations, such as this fracture simulation from Vikas Srivastava's lab in Brown. Again, this presentation would be incomplete if I don't talk about model-free methods. This is a totally model-free, as the name suggests. It doesn't assume any model. It was proposed by Professor Otis's lab at Caltech, and the idea is to not use any model, but using experimental data itself as the constitutive model. And in every step of the simulation, it works by using the k nearest neighbors, finding the solution by looking at the point closest to the experimental data. And the last area I'll talk about is the accelerated characterization and discovery, which is a result of the whole innovation space that machine learning is allowing us to have. And one enabler of that is the fast automated constitutive and computational modeling, but another enabler is the adaptive experimental design. So traditionally, how we develop models and materials is that we synthesize materials, run the tests, do the modeling. But this method is turning out to be inefficient for many modern materials, like metamaterials, 3D printed materials, where the input space, the geometric space of the materials is huge. They can be made in millions of different ways. And so if there are too many inputs, we need to run too many tests to fully characterize these materials. And suddenly we notice that for many types of materials, we would require millions of experiments to fully characterize them, which is very inefficient. So adaptive experimental design is helping us make our experiments very efficient by a class of method called Bayesian active learning. The idea here is to train a statistical model between the input and the output space, and then using some information gain criteria to predict the next set of geometric and loading conditions for evaluation. So this iterative method allows a very efficient model development from a number of experiments that is several orders of magnitude. It can be less than the traditional full factorial experimental design. And this adaptive experimental design and adaptive approaches have been used now in the literature to discover many different types of materials. For example, this GAN-based research on metamaterial discovery from LSU. Also, I'd like to mention this Professor Wei Chen's research from Northwestern on topology optimization using the integration of neural networks with Gaussian process regression. And not only at the macro scale, machine learning is allowing us to discover materials at the micro scale, such as this genome tool, which has so far, I think, discovered 2.2 million stable crystals out of different combinations of atoms. So machine learning methods are able to now parse through hundreds of millions of possible atomic arrangements, and some of these materials are now being made by experimentalists for their optimal properties. All right, with this, I would like to quickly summarize. I talked about the application of machine learning for mechanics of soft materials, but in solid mechanics in general, how it's helping in constitutive model development of soft materials, making our models more flexible and more accurate and more automated. How data-driven approaches are helping us understand the uncertainty in our computational model and making them extremely fast, and some emerging areas into how scientific ML is helping every stage of a model or a material development, from synthesis to characterization to constitutive modeling to actual simulations and even the actual deployment of the material in its workplace. All right, so I'd like to acknowledge my students, my advisors, my collaborators, and the funding support. And I'll stop with the slide. I'm looking for a postdoctoral researcher in the space of data-driven constitutive modeling and model discovery. So if any of the graduating students are interested, or if any of my collaborators here have students who are graduating, let me know, and I would love to talk to you. So with this, I would like to thank all the organizers for inviting me, and I hope you learned something about the data-driven modeling space in soft materials research. Thank you.
Thank you so much, Kshitiz. This was wonderful. Uh, I think we already have questions from Rakesh. Rakesh, you can unmute and ask your question.
Thank you for that. That is a great presentation, and uh, my curiosity in, like you told that uh, that Gaussian process regression can predict the exact prediction. It can do exact prediction. So can you elaborate that part? Like, what do you mean by
Yeah,
exact?
yeah, I can. Yeah. So in Gaussian process regression, there is a parameter, it's called the nugget parameter. So this is the kernel, but then there is this plus term here where there is this nugget parameter, and that captures the uncertainty in the prediction. And that nugget can be changed or tweaked as a parameter to ensure exact inference. Now, what I mean by exact inference is, for example, if you see this plot here, this blue is the training data. Okay, so at the training data, you see that the GPR is exactly predicting that value, right? So if I have this blue as my training data, I can make the GPR exactly predict that. That means if I have zero stress and zero strain condition in my training data, I can make sure I can be assured that the GPR model will always have a fixed reference state. And that is important for numerical stability, right? There won't be any stress for no strain, or there won't be any strain for no stress.
Okay. So I have another question regarding modeling of uh, the stress strain curve of any material. Like you have shown for the soft matter, and also if we think about the metals, like
Mhm.
few metal, lot of alloys are there. They show like phase transformation during tensile loading or during loading basically, or by if we give heat to the material. So
Yes.
then how it can learn that those complex phenomena. And also
Yeah.
for, if we think about micromechanics, there will be dislocations theory and movement of dislocations. Then how it could learn that thing.
Yeah. Oh, that's a good question. So this framework that I presented, okay, I'll make sure I remember both parts of your question. Okay, so let me that I properly answered. So your first question was about metals, and the second question was about the micromechanics. Right? Okay. So this framework that I presented today is on viscohyperelasticity. It is specific to soft materials. Okay, so you can't use this framework for metals. It's not going to work. It is specifically for short time viscohyperelastic response where the material has a fixed reference state. Now, the thing with metals is, especially the shape morphing metals or the shape memory metals, they don't have a fixed reference state, right? Depending on the temperature, depending on the conditions, they can have different reference state. They can change the shape. They can remember their shape. And a lot of history dependent processes are happening. So this modeling framework is not for metals. It's not for, it's just for short time viscohyperelastic materials. Now, that doesn't mean that we can't develop scientific machine learning based approaches for metals. In fact, towards the end, yeah, you should probably read this paper. So in this paper, the authors used ANN to learn this model for shape memory polymers, shape memory alloys. So this is a model for metals. So if you increase the temperature, the material goes phase transformation, and the strain changes, right? So this type of modeling framework needs a history-dependent component. So it needs a component for history, and I think this one also had inclusion of internal variables, which again my model right now doesn't include. So different machine learning methods or different approaches have to be used for different material classes. So I don't think there is a material agnostic model yet. Maybe it shouldn't be there anyways, I think. And regarding micromechanics, again, this model that I presented does not capture micromechanics. One promising approach in the literature, it's called a approach called CANs, constitutive artificial neural networks. So if you look at their papers, you will find one of the papers where micromechanics is one of the, or micromechanical parameters or features are one of the inputs in the model. So I advise you to look at the papers on constitutive artificial neural network, or CANs.
Thank you very much. Can I ask one more question?
Oh yeah, sure.
Go ahead.
So basically, I am curious about it. Like if we train on two different metals, let's say any two metals, and can it learn the alloy behavior?
Again, as I said, this model that I presented today doesn't work for metals. It works for short time viscohyperelastic responses of soft materials. Now, that answer, it's not a straightforward answer. Okay, first of all, it's an active area of research. You should read the CAN paper or other papers that try to incorporate microstructure. Maybe there is a way to do it, maybe not, but I don't think there is a straightforward answer. At least I don't know.
Okay, thank you so much. Thank you so much for the
You're
great
welcome.
presentation.
Chin Young, you had some questions?
Yes. Thank you for a great talk. I have a question about how we use the GP on on-screen quantification. So in your first work, you show your GP prediction, and I noticed, like, I think you showed the mean prediction without showing the uncertainty. And in the second work, you show use GP as a surrogate to predict the uncertainty from different with different the range of different input variables to predict the uncertainty. So what's your thoughts on utilizing the GP uncertainty to predict, that uncertainty in your second work?
So yeah, the two works I showed had a different application. So when it comes to constitutive modeling, the way GPRs have been used is to predict the stress strain response, and that goes more along the mean predictions. So that's why I showed you the mean predictions. But if you read my actual paper, in the supplementary material of that paper, I show all the uncertainty bands as well. So uncertainty is, it's not a lot in the training regime, and in the testing regime, it will be a lot because we are not in we are outside the training regime. And the second application, that application specifically was uncertainty quantification, right? So there we harnessed the GPR for UQ. So this actually honestly shows how powerful GPR is. It can be used as both a constitutive modeling framework, and it can also be used for uncertainty quantification.
Yeah, my point is that basically in the sex, for example, for the second work, the
Yeah.
GP uncertainty itself
Mhm.
is not used as a input to quantify your uncertainty.
Yeah.
Do you have any thoughts on that? How can we utilize that GP uncertainty to evaluate the uncertainty in the second work?
That's a good point. I have no immediate thoughts on it. I haven't thought
Mm,
about it. Yeah, but if you have, we should talk. Yeah,
mm.
but we didn't use it. We just used the mean GP prediction uh, across tens of thousands of surrogate simulations. We didn't use the mean the uncertainty.
Yeah, because we sometimes when we claim the advantage of GP, we also mention uncertainty. But
Hmm.
I still in uncertainty quantification, we still use the mean. So I'm thinking of ways
Yeah,
to how do we utilize the GP uncertainty to quantify uncertainty.
yeah, yeah. No, that's a good point. Yeah, I
Uh,
haven't thought about it.
yeah. Thank you.
Thank you.
Thank you very much, everyone. Are there any more questions?
Maybe I will ask one quick question and
Sure.
then we can wrap up. Yeah. So yeah, nice talk. So one question I was thinking, but maybe before that, to add to the last question. So I think if you want to quantify the GP uncertainty and propagate it, there are two ways. If the system is linear, GP is Gaussian, the output will also be Gaussian. So that becomes you can get closed
Yeah,
form. But in most cases, the system will be non-linear. So in that case, you have to
yeah,
sample the GP and do MCS over that. So this is to answer Chenian question. So there is some paper which has done it in general. So you can sample the GP. Each realization will become a deterministic thing, and then you can do. So that will give you the total uncertainty, the epistemic uncertainty because of limited data in the GP, and obviously the because of whatever the parameter material in this case is uncertain. But yeah, my question is something else. So because it was just before me, I thought that let me add it to that also. So you
hmm
use constraint GP, right? In the third variant of the GP that you showed in the first part of your talk, that was
yes,
constraint
yes,
GP, where you solve the
yeah,
GP under some, say, non-negativity constraint or something like that.
yes.
So please correct me if I'm wrong, but that will only ensure that the constraint satisfied for the training data.
Yeah.
During inference, that need
It is
not be
it is
satisfied,
enforced in the
right?
training data. Yes, it is enforced in the training
But
data.
not
Yes.
yes, but not in the testing data or the during inference, right?
Yeah, but it leads to hyperparameters that at least obey
Yeah,
that
obviously.
in the training data, and we have found out that if we add the constraint, it makes a difference even in the testing data. So the hyperparameters that come out of the constraint optimization uh, do better than the hyperparameter, even in the testing regime for the constraint than the hyperparameters would if they were trained
Yeah,
without any
yeah, yeah.
constraint.
So I'm asking because I'm yeah, yeah. So I asked this because I'm relating it with, let's say, the invariant neural network and the polyconvexity, the way they enforce, right? With
Mm,
neural network, it can be guaranteed even during inference with certainty. But obviously, GP is much more faster within small data regime. It will give you the uncertainty. Those are the advantages. But yes,
yeah, yeah,
trying to draw a comparison between the two.
yeah.
And yeah, the other question I had, you already answered. So I was wondering if someone is working on developing a foundation model for constitutive relation, like let's say multiple material, can there be a single model? But you already answered that. So
Yeah.
I'll skip that.
Yeah.
So yeah, again, thank
Yeah.
you for
Even
attending
the
and
universal model
wonderful
where
talk.
people say universal model, they're still universal for a material class. So I think
Yes,
it's
yes.
very hard, or I don't know if it's even a good idea to develop a model for everything.
Yeah, 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 yeah.
Yeah, because the physics is
Maybe for
different.
HCC, BCC, I think those
Yeah,
classes
exactly.
there are some,
Yes.
but not
Yeah.
the general one. Right.
Yeah, exactly.
Uh, yeah, yeah, yeah. Okay. So that's all from my end. Somriti, if you have something you can add or you can conclude. By the way, next
Yeah.
week's Sid Kumar is our present is our invited presenter. So you mentioned about Euclid, right? So
Yeah.
that was by Sid Kumar, right? Sid Kumar Lawrence is a
Yeah.
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 Yeah. Laura was here in Minnesota last week.
Oh,
Oh,
okay.
okay.
All
Kshitiz,
right.
I
Yeah.
think,
Thank you all for inviting me. And
thank you
as I
so
said, I'm looking for a postdoc. So if you guys have any graduating PhD students interested in this space, send them my way. Just we can talk more.
Absolutely. Thank you so much, Kshitij, for the wonderful talk. And we look forward to meeting all of you again next week. Thank you.
Bye bye.
Thank you.